Good morning, everybody. All right, so today, finish up chapter 9. I want to do another example of an elastic. I want to talk to you about elastic collisions. We're going to deviate from the book here, and then we'll get into chapter 10. So that's sort of the rough idea of what we are going to be doing. Back in chapter 4, our projectile motion chapter, we had a problem where a car rolled off of a cliff. And I use that as an example where we had to set up two different problems, right? Two different accelerations, all that kind of stuff. Well, this problem doesn't have anything to do with projectile motion, but apparently the same motorist is having fun. This time, right, car's rolling down a hill, a slope, an incline, and collides with a truck. So the way that you know when you need to use conservation of momentum outside of chapter 9, right, is when you want to figure out what's going on in a collision. And by collision, I mean any interaction between two objects. Before chapter 9, we always said, okay, well, it's the speed of the ball just before it hits the ground, right? Or, you know, we're going to ignore what happens after it impacts. Well, now we can do those impacts because in these collisions, when objects come into contact with each other, we can use conservation of momentum, figure out what's going on. Remember, it's a sandwich, right? We gotta figure out like before and after and during the collision itself. So I start with a visualization. I got to get started with a picture, right? So let's see, got to get a hill. Oops, got to get a hill. Oh, that made a triangle for me, yay. All right, and then let's see, we need car. And the car is going to go down the hill, and then the car is going to hit a truck. I'm trying here. I'm trying to do a little bit more than a, free body diagram. And then, so I've got like before, during, those should be like, right? And after, okay, so like, what do we think, what do we know about after? Like, what's the car doing after this collision? It bounces back. How do you know it bounces back? What word is it using? Rebound, right? A rebound is a bouncing backward. So we could have drawn this completely the other way. It would have been fine. And I just need to make sure my directions are all good. So like before, right, it comes in and this thing isn't moving. But after, we know the car, right, is heading backwards. And then our goal is to find out, right, what the truck is doing, right? What's going on after that? So let's see, what do we know? We know the mass of the car, we know the mass of the truck, but the only thing they tell us is that we've got a 5 meter per second rebound. We've got to be careful with directions. Momentum, velocity is a vector, all that sort of stuff. So what do we want to call that 5 meters per second if it's like bouncing back? It just kind of feels natural to call it negative, right? So the implication there is if we have a velocity that is moving to the right, it better have what sign on it? A positive sign, right? And so we just want to be careful with our signs as we set all of this up. Okay, so kind of 3 parts here, before, during, and after. And I start in the middle of the sandwich, right? I start with my conservation of momentum. I've got 2 objects hitting each other, doing something. And so I'm going to start there and then go see what I need to find, right? This is going to guide me in the other parts that I have to do and figure out my pieces of bread. So let's see. This car's rolled down, and I've got to ask myself a question. Before the collision, like the instant before the collision, does anything have momentum? What's moving before the collision? the car. So we're going to write down mass car, velocity car, initial. All right? We'll go ahead and put a vector sign over it, and then we'll take those off in a second. That's the only thing before the collision, right? After the collision, what has momentum? Both the car and the truck. But they're not together the way our last example was. These are separate objects doing separate things. So I'm going to write mass car, velocity car, final, plus mass truck, velocity truck, final, right? Now, what are we after? Find the velocity of the truck after the collision. This is what we want, right? We're going for that thing right there. Do we know the velocity of the car final? Yeah, right? It's not 0. What is it? -5, right? And then what about, so we know all the masses. What about the velocity of the car initial? Do we know that? No. Okay. So this is telling me, right, that I've got to find this, right? I want what's in green, but I'm going to need to find the velocity of the car initial before I can find anything else. The mass of the car, velocity car final, those are all known things. Yeah?
Just curious. It says parked the car, so how come we wouldn't?
Well, it's parked up here, right? They parked on a 25-meter high hill. So that's 25 meters right there. Okay, and it's going to roll down. And so in this collision right here, right before they collide, I need to find the velocity. Okay, so I take a break, right? I'm in the middle of my sandwich. I figured out that I'm missing the tomatoes, and so I've got to go find the tomatoes. Is this am I pushing the analogy too far? Probably. Okay, but how am I going to find this velocity car initial? So this is where I reach for a different toolbox. It can be kinematics, it can be Newton's laws, it can be energy. I'm going to use energy, okay? Because I know the vertical height where the car started, right? And all I want to know is how fast the car is going when it gets to the bottom of the hill. So I can set up a quick conservation of energy where I've got like an initial, and I've got a final down here. I'll put 0 down here. Are there any springs? Thank goodness. So work other plus energy initial equals energy final. There's no friction that they tell me about. And so my initial energy is mgh. My final energy is 1/2 mv squared. I'm doing this pretty fast, right? Because we've done a lot of these, okay? And then I solve for the speed. Well, that's 2gh equals v. What happened to the m's? Yeah, they're same on both sides. Be careful. You can't cancel these masses, right? Because they're different. All right. So I'm left with v being the square root of 2. Boy, we keep running into the square root of 2gh, don't we? Square root of 2gh. The speed at which things will be going if they roll down a hill. The speed that a ball gets dropped. It can be hard to accept that those are the two same things. That's the answer if there's no friction, right? If there's no sliding, there's no pushing, there's no other forces besides gravity turning the speed into, turning the potential energy into kinetic energy, then the answer is always the square root of 2gh. I've started putting down when I don't know answers, the answer is either 42 or the square root of 2gh. Only 3 people got that reference. 42, what's 42? It's the answer to universe. It's the answer to the question. No. Darn it, what's the question?
Meaning of the universe.
Oh, that's right. What is the meaning of the universe? The answer was 42. From the Hitchhiker's Guide to the Galaxy, right? And then they had to go build a computer to figure out what the question was. Okay, so I know that initial speed is going to be the square root of 2gh. So now we can throw in some numbers, right? 2 times 9.8 times 25. And I got 22.8 0.14 meters per second. So that speed coming out of my before section here that I've done in blue becomes the initial speed for my middle of my sandwich, right? So I know that this number is now 22.14. Okay, so I think now I can go ahead and solve for velocity of the truck final, right? I can throw some numbers in here. So mass of the car, 1,500, right? Velocity of the car initial, plus 22.14. Do you see how I went from a thing that's a vector, had a vector arrow over the top. When I turned it into a number, what did I make sure to include? The sign, the direction that that thing was going, right? It's moving to the right. I've called right positive, so I better have a sign on it. Equals 1,500 times minus 5. Again, where'd that minus 5 come from? The direction, 5,000. And now I'm going to take the vector sign off there, okay? I'm going to go ahead and take the vector sign off. I just take it off. It's neither positive nor negative. I'm going to let the math work its thing, and if I've set this up correctly, I should end up with a sign that will tell me what direction the car is going. Now, can you take a guess as to which way the truck will be going after the collision? It's probably to the right. So we expect this answer to come out positive, right? Don't confuse your intuition or expectation for what's happening, right, with letting the setup work itself out. What do I mean by that? Don't put a sign on an unknown. You can just take the vector. If it's an unknown quantity, just take the vector sign off, let the math work out, and then do a check, right, with what you expect to happen. So no putting like if you knew that the truck, if we were doing this the other way and they told us the truck was moving to the right and we suspected, right, that the car was moving to the left and they asked us to find the velocity of the car after the collision, don't artificially include a negative sign on an unknown thing because you're double correcting at that point. Just if it's unknown, strip the vector sign off it and let's see what happens to the math here. What happens to the math is this is 1,500. 22.14 plus 5. I did a couple of math steps there. I moved the 1,500 times minus 5 over to the other side, and then I factored out the 1,500. Right? So it became positive, and I factored out 1,500. It's supposed to be a 22. And then I divide both sides by 5,000. I'm showing you more numbers right now because I'm about to do a bunch of symbolic things you're going to hate. So I'm just buttering you up here. What is this? So what is this number? I got positive 8.14. Okay, so we can check this a little bit. Did we get the direction we thought we were going to get? Yes, right? So I'm feeling kind of confident, right, that this might be the right answer, okay? So, but it seems a little, I don't know, to me it seems a little high. I'm kind of thinking, wow, the car only came in with 5, well, it came in with 22, so I guess maybe it's not too high. I was thinking it came in with 5. But it came, so why isn't it like bigger than 8? Why is this truck's speed lower? Because it's mass, right? It's got a heavier mass, right? If the truck were less massive than the car, I'd expect it to like really bounce out of there, right? So I'm kind of like, okay, now that I've considered sort of the order of magnitude of numbers in the problem, right? The fact that it rebounded off, I could be convinced. And that's enough of a check for me. I'm not an engineer. But again, yes?
My question was, why did we multiply the 1,500 times 5 instead of adding it to the other side?
In other words, what did I do with this?
Yeah.
I did add it. I moved this over. It's a negative thing. It becomes a positive thing. And and then I factored out the 1500. I have a tendency to skip math because it's painful to me. I'm about to prove that statement wrong on the next slide. The purpose, again, of this example was to show you that kind of sandwich method, right? And then show you that conservation of momentum is what's happening during the collision. What happens before and after is not chapter 9. Now, in this example, I really didn't do an after. I think in your homework we give you a couple problems that are like, like the truck goes over a rough patch, find out how far it slides, right? Again, that's a conservation of energy friction problem, right? So they're just being extra painful in the homework. I know, I picked it. It's my fault. All right, so what I want to do now is talk about elastic collisions. What's the difference between inelastic and elastic? Conserves kinetic energy, okay? And the key thing there is remember that we're conserving kinetic energy. Well, we're always conserving energy. In an inelastic collision, the kinetic energy before and after does change, meaning that work other happened. There was sound, there was vibration, there was deformation, there was heating. A bunch of things can happen in collisions. But under the perfect circumstances where we conserve not just the overall energy, which always happens, but specifically kinetic energy, let me show you what happens. So I'm going to write this out in full in its most general form. So we have conservation of momentum, which always happens regardless of the kind of collision. But for elastic collisions specifically, we also have conservation of kinetic energy. So let's write down those two statements. And I'm going to do the idea I have in my head is that we've got like one object that's moving one way, one object that's moving the other, and then they collide, right? And they end up, either bouncing off each other. I suppose we could have a situation where, like if one's much bigger, they both end up going this way. We want to be able to predict what's going to happen after the collision, right? Our goal here is to find out what these two final velocities are if we know the masses, right? And if we know the initial velocities. So what's that going to look like? Well, before the collision, both objects have momentum, m2, v2 initial. And after the collision, because in an elastic collision, try to say that really fast, things don't stick together, ever. Sticking together is inelastic. m1 v1 final plus m2 v2 final. This is an equation with two unknowns in it. We don't know what the final velocities are for the two objects. And so all by itself, it's not enough to be able to figure out what's going on. We're going to get our second equation from the conservation of kinetic energy equation. 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared. Oh my gosh. m2 v2 final squared. Okay. Again, we don't know v1 final and v2 final. Those are our unknown things that we want to solve. Okay. We know the masses and we know the initial velocities. So the reason I'm calling it the magical mathematical method at the top of the slide is that this is where I'm going to deviate from your book and most physics textbooks, because I believe they do it wrong. Like their physics is good, the physics is fine. It's the way that they go about the next few steps that I feel does a disservice not only to you, but to physicists and physics education in general. What do I mean by that? If you go look at the section on elastic collisions, I think you'll see like 6 to 8 equations for the final velocities. And these equations are kind of all over the place. And the problem is they tend to, each equation is like, well, this applies to this situation. And oh no, this different equation applies to if one of them's not moving. And like, they end up with all of these equations. And then some textbooks even put like plus minus in the equation. I never know idea what to do with that. And so I want to show you a different way. Again, the physics, the underlying physics here is the same. This is just a, what's that word? A semantic difference. Semantics, that's a fancy word for word choice. Like what words do you use to describe something, right? So this is a mathematical semantics. I'm going to do math a different way than most of the physics textbooks do it. It's not advanced, it's just different. And we're going to come up with really one equation to rule them all. I try, you know this theme, and it's not just me, this is just a physicist's way of thinking. If we can solve all the problems once, we will do that, right? And then we can apply our toolbox to whatever situation we've got. But we just want to be able to solve it once, if we can. And in this sense, we can. So, for the next 5 minutes, you don't have to write down anything if you don't want to, okay? Because I'm going to do a derivation. I rarely do this in here, but I will never ask you to repeat this derivation. But I know there's several math majors in here. I know some of you are closet mathematicians and just don't want to admit it. And so this is for you. I'm going to show you. And now, you might want to write down notes about like the method, because this can save you from some really nasty algebra. I'm going to show you a trick that can save you from tons and tons of algebra. And I don't know a single person in the universe that wouldn't go for that, right? Save me time on algebra? Yes, please. Okay? And it's not called Wolfram Alpha. All right. What's the problem? We have 2 equations with 2 unknowns, right? We have those unknowns, same unknowns are over here, I have 2 equations, 2 unknowns. Those of you with some mathematical inclinations, can you see the writing on the wall? Can you see what's going on? Let's just paint a picture for how bad this could go. I want to solve for V1 and V2. What do I do? Okay, so like solve for V1 over here, right? Okay, so that's going to move this term over here, and I'm going to have 3 terms over here, aren't I? Okay, so now I know what V1 is, and so I would plug that in over here. That's 3 terms squared.
Well, they're all divided by something too.
Okay, it's bad. But the specific badness here, okay, is that what happens if you square something with 3 terms in it? You get 9 terms, right? If it's a 2-term thing and you square it, you get, what is it, 3 terms? Maybe 4, okay? But this one, you get like 9, okay? And what's worse is some of those terms will have your thing that you're looking for by itself, but then others will have them mixed and then mixed with squares. Like it's bad. It's really bad. The way that they taught you to do it is a bad way. There are better ways. And so let me show you the power of math. First of all, we're going to clean this up. I don't like these stinking halves everywhere. Why can I get rid of them? Because I say so. No, because they're in every term, right? Multiply every term by 2, gone. Okay, we're going to massage this just a little bit. M1 V1 initial minus squared minus M. What am I doing? That's right. I'm going to pull everything with M1s to one side. M1 V1 final squared. So I moved the M1 V1 right over here, becomes negative. I'm going to move the M2 over here. And it's going to pick up a minus sign also. So let's see, what does that leave me with? M2v2 final squared minus M2v2 initial squared. Okay, I did that right. I left the squared off. Okay, so there we go. I've gathered all the M1s on one side and all the M2s on the other. Okay, I'm going to do the same thing over here on the left-hand side of the screen. We're going to get all the M1s together. I'm going to go ahead and drop vector signs for now. It'll be okay. It'll be all right in the end. I'll show you. Minus M1 V1 final equals M2 V2 final minus M2 V2 initial. Okay, it's the same step. I'm just kind of getting all the M1s on one side, all the M2s on the other. Now I can factor out some M1s. I get V1 initial minus V1 final. And you're like, Mr. Balogh, why would you do? You'll see. You'll see. Okay, so just factoring some stuff. I'm going to do the same thing over here. Just factor M1 V1 initial squared minus V1 final squared equals M2 factored out V2 final squared minus V2 initial squared. Okay, so I haven't improved things much, right? I've just sort of manipulated and factored and moved things around. There's not much going on here. And it might look like I've made it kind of harder to solve these things now because I still got the squares. The whole problem are the squares, isn't it? That's really where the problem lies, is that we've got unknowns that aren't squared, we've got unknowns that are squared. That's just a big mess. But there was a rule way back in your deep, dark algebra days, wherever you were, high school, college, kindergarten, wherever it is you start algebra now. And it involved the difference of squares. And you're like, I knew you were sitting there that day going, when am I ever going to use this? Math teachers rejoice. The time has come. Because a difference of squares, something that looks like x squared minus y squared, you can rewrite that without the squareds in it. Does anybody remember? X plus y times x minus y. Boom. Squared's gone. M1. So what does this become? V1 initial minus V1 final times V1 initial plus V1 final, right? And then this one, same thing happens. V2 final minus V2 initial times V2 final plus V2 initial. And you're like, Mr. Balogh, where'd that get you? It just got worse. Well, it didn't. Because now I'm going to do something amazing. Something that you may or may not know was possible to do. Come on, let me select that. There we go. I'm going to copy this because I'm just going to keep that there. Copy, paste. So fun to see old people use technology. Okay, so all I did is recopy this line right here. That's all I did. Okay? Because now I'm going to take this right here and I'm going to divide it into that one right there. You're like, whoa, Mr. Balogh, you can't divide equations into equations. Yes, you can. It's called a ratio. How do you divide an equation into equation? You divide the left side into the left side, the right side into the right side. Just hold on. Just hold on. So let's copy that and then paste it here. Oh, put it right there. Draw a green line so it looks like division. Okay? And now that I've done that, and this dividing equations into equations thing works all the time. It's fantastic. If you're stuck on some algebra, just hold in the back pocket. Wait, Mr. Balogh one day said I could divide equations into equations. Just do it, see what happens. It can save you from the algebra jungle. There's big snakes and spiders in there. It's really bad. Okay. So, what cancels? Do you see it? Do you see it? Okay, first of all, the masses go away, right? But then this whole term just poof, right? And that one, poof, poof. Like all of a sudden, what looked like horrible math becomes a statement of V1 initial plus V1 final equals V2, I'll just write initial plus V2 final, because I can put the positives in any order. That thing in the box right there. Now, okay, pick your pencil or pen back up and start taking notes again. Because the thing in the box at the bottom of the screen is what we want. It's the only equation that, back up, rearrange that sentence. This equation only works for elastic collisions. This is the big caveat with this equation. It's a magical mathematical result, but elastic collision, I don't know if I spelled that right. There's an I somewhere. Collisions only. I do not want to see you using this equation on an inelastic collision. I'll kill you. Yes?
So the left, P initial equals P final, that represents what again?
This thing in the box?
No, just the left equation is like, how are they related to each other?
I'm lost.
The P initial equals P final, and then the kinetic energy initial equals the kinetic energy final.
Yeah.
Are they related to each other?
Well, only in the sense that in an elastic collision, they're both conserved. So they're both statements that are true for an elastic collision. I can take advantage of that and set up two equations with two unknowns.
So that's why you're able to kind of divide them by each other?
The reason I'm I can divide any equation and form a ratio. I've just formed a ratio. We do it with derivatives all the time, right? So yeah, ratios are fair game for anything. Not sure I'm fully understanding or answering the question that you're asking, but I'm going to move ahead anyway. This equation in black, coupled with the conservation of energy equation up here, can solve every elastic collision. Those are the only two equations you need. And it works for every situation. For example, if mass 2 were not moving, what would you put in for its velocity? Done. What if mass 2 were not moving to the left and were moving to the right? What signs would you put on the initial velocities? Both positive, right? The way I've got it pictured up here, you would make V2 initial be negative. Why? It's the other direction from V1 initial, right? So as long as you're careful with the directions that you are putting into these equations, the two black boxes can solve every elastic collision you ever run into. And you don't need the 60,000 equations that they give you in the book. Okay? You'll go onto websites and you'll see tons of equations for different situations. I don't know why they're there. It's like they're afraid of cool math. Math does have its uses. And sometimes even all those identities and whatever they taught you. Does anybody have like PTSD over trig identities? I know I do. Oh my gosh. There's only one trig identity you ever need to use. Cosine squared plus sine squared equals 1. That's it. Everything else, every once in a while it's the, what is it? 1 minus sine squared theta is equal to cosine 2 theta or whatever that one is. Right? The double angle, the angle, sometimes those come in useful. The rest of them, nature ignores. All right. So let's use these, right? Let's use these equations that we've developed, well, the one we developed, okay, with an example of doing an elastic collision. How do you know it's an elastic collision? In this class, at this level, they will tell you. Okay? If you are not told what type of collision you are dealing with, what do you assume? Inelastic, and you don't use the equation we just developed, right? So you have to be told. In the real world, it's always inelastic unless you're doing stuff in outer space or with magnets. Okay, so 2 bowling balls. We got to visualize. Bowling ball number 1 with 8 kilograms, right? They're colliding head on with each other. Doesn't really matter which one I put moving left or right. This will all work out. Okay. Now notice they said the lighter one is moving at 5 and the heavier at 2. What are they trying to trick us with? If they're going to collide head on and this one's moving at 5, what do we have to put down for this one? -2. Do you see how they didn't say -2 in the problem? They just said it's moving at, right? They gave you the speed of the ball. We need to be careful with directions, don't we? And I'll just put units on it because I'm a unit person. Okay, that's what's going to happen, okay? And we want to find, like, after they collide, and my assumption is they'll bounce off of each other. Maybe they won't. Again, what we just developed handles every situation. Bouncing off, one of them continuing in the same direction, doesn't matter. Okay, so this is how you do it. Okay, for an elastic collision, you write down conservation of momentum, kind of the middle of the sandwich, and then you write down V1 initial plus V1 final equals V2 initial plus V2 final. Easy to remember, right? Okay, 1's initial final equals 2's initial finals, right? Okay. The one on the left needs a little bit more development. What has momentum before the collision? Both of them. M1 V1 initial plus M2 V2 initial. And then afterwards in this problem, well, I guess in general this is always, you can always write this down first step. V1 final plus M2 V2 final. You're like, Mr. Bennett, I didn't put vector signs on. Okay, fine, I'll put vector signs on. Okay. But now, my advice to you is just put numbers in. Don't try to do this symbolically. I won't even try this symbolically. It's too many symbols. You end up with chapter 9 elastic textbook problems. So what I do is I'm just going to drop numbers in now. Mass 1 is 8. What am I going to put in for V1 initial? Positive 5. Plus mass 2, which is 10. And what am I going to put in for V2 initial? -2. I'm minding my directions. Okay, and then I'm left with 8 times V1 final plus 10 times V2 final. So again, V1 final, V2 final, those are my unknowns. Right? Those are the things I'm looking for. Okay. Over here on the right-hand side, V1 initial plus 5 plus V1 final minus 2 equals, no, Mr. Balogh, you did that wrong. Plus V1 final, which is what is unknown. V2 initial is minus 2 plus V2 final. Okay, there we go. Notice I've dropped my vector signs over the tops of these. I could carry them all the way through. Point is, I just don't want to keep writing that vector sign. It's going to work itself out. If I get a positive, it means it's moving to the right. If I get a negative, it means it's moving to the left. Okay. What do we do now? In Great Britain, they would say we would do maths. Maths. 8 times 5 is, I don't know, 40? -20, 8, and 10. Okay, I'll clean that. That's 20, isn't it? And then there's 8 and 10 over here. I'm going to get a little bit sloppy because I'm going to divide both sides by 2. So that becomes a 10, that becomes a 4, and that becomes a 5, doesn't it? So I've got 10 equals 4 V1 final plus 5 V2 final. I'm just cleaning up a little bit, trying to get as low as I can go. All right, over here on the right-hand side, let's see. What do you want to solve for first? V1 or V2? You want to solve for V2 first? So we'll eliminate V1, V1 final. Let's see, that's going to be, is that negative 7? How do I get negative 7? Positive went over to the other side, became negative. I already have a negative 2 there, don't I? So negative 7 plus V2 final. So now I go ahead and I grab my V1 final, and I'm going to chuck it into there. Right? Just going to make that substitution. So what is that substitution? It's going to be 10 equals 4 times a negative 7 plus V2 final. So that's my substitution, plus 5 V2 final. That was sloppy. 5 V2 final. So what happened there? I took V1 final, and I shoved it in there to get this. Okay. Clean up on aisle 5. What's 4 times minus 7? Plus 4 V2 final plus 5 V2. What's 4 plus 5? It's 9, isn't it? V2 final. This turns into, is this 38? Yep. And what's 38 divided by 9? 4.22? Sweet. Positive 4.22 meters per second. What does that mean? What's the positive sign mean? It means this one bounced off, didn't it? V2 is going the other way. All right. How do I find V1? Right. V1 is going to be negative 7 plus 4.22, or negative 2.78. And what does the negative sign mean? It's going left. Bounce off. I'm done. I didn't have to use 60,000 equations in that section of that chapter. I didn't have to guess which equation was right because this equation and this equation can solve all elastic collision problems. It's just amazing. I don't know why we don't teach it like this in books and on the internet. Should I start a website? Charge $5 for this? No. What? My YouTube channel that I make exactly $0 off of because I don't monetize it. So for any elastic collision problem, even if things aren't moving, like if an object isn't moving initially, what are you going to put in? 0. If they tell you that something stops after the collision, what are you going to put in for its final velocity? 0. And then for anything else, just be sure to mind your directions. Make sure that if something is moving to the right, you call it positive. Moving to the left, call it negative, right? Be consistent with your choice for what's positive and negative. Be intentional about your choice of directions. And you'll be all right. All right. That was chapter 9. That's the end of the toolboxes. I mean, there's going to be more toolboxes. But like kinematics, Newton's laws, energy, momentum. Those are the toolboxes of mechanics. Technically, you could say that there's one more toolbox in mechanics. It's called simple harmonic motion. But here at Fresno City College, we don't cover that until Physics 4C. We lump that together in Physics 4C because the applications of simple harmonic motion turns into waves and sound, which then goes perfectly into optics for light. We just like having all of that together in Physics 4C. So there are other, what we call classical physics involved. But for Physics 4A, the rest of the semester is applications. We're going to take all of these toolboxes that we've learned about this semester. It's taken, are we in the 10th week? It's taken us 10 weeks, right? And we're going to apply them for the remaining 7 weeks. 18 if you count the finals week, right? So we need to begin, right, in chapter 10 by talking about circles for realsies. Your author has decided, and I don't disagree, I kind of like how the author kind of warms you up to the idea of circles as we go, because we've done some circular things, right? We're just going to be very exacting now and make sure that we know what we are talking about, right? Because what we're going to do in chapters 10 and 11 is we're going to take all of our toolboxes and specifically talk about how to do it with this, right? With a wheel, with something moving around in a circle. We're going to start purely with just things that are rotating. Eventually we're going to get to the point where we'll have them rolling across the ground, okay? But we want to deal with rotation specifically because so many things in our lives rotate. Even things that don't look like they're rotating are rotating. Trust me on that one. So let's begin. We're going to go all the way back to the beginning. Back when you thought physics was hard. Chapter 2. All right? And in chapter 2, we laid down a way of talking about like where we are and how our position changes, which is velocity, and then how velocity might change, which is acceleration. And I know a lot of you are still shaky on the whole, what's the difference between velocity and acceleration thing. But now's your chance. Now's your chance to really get it to sink in. However, we need to talk about it in the context of circles. So like the question becomes, how do you know where you are on a circle? I mean, what's the difference between like being here versus there? How do we talk about where we are in a circle? We need two things, right? And they're not X and Y. Yeah. Yeah. Say that louder. Polar coordinates. And the little piece of you died inside, didn't it? Right? And why am I smiling? It's the rictus of death. No. I'm going to tell you a secret. Polar coordinates aren't that bad. They really aren't. I know they tortured you with them. But they're actually really useful because they're a natural way to talk about circles and things moving in circles. So let me see if I can't convince you just a little bit. You need two things. If I want to know like that point on that circle, I need to know how far away from the center of the circle I am, and I need to know what angle I'm at, okay? The part that gets me about polar coordinates is that, well, quite frankly, they're a little bit weird. What do I mean by that? How do I talk about the distance that this thing went? Like if it started right here on the positive x-axis and then went up there. In other words, like on my wheel, right? If I take, this one doesn't have a sticker. Where's my tape? So if I take a piece of tape, blue tape, right there. Quality stuff here. It was probably dusty. But. Okay. If I take my piece of blue tape here, which I don't know which side it is, so, and I'm going to put it on the positive x-axis, right? Okay. And then I rotate it up, and it goes up to here. How far did it go? 90 degrees. Pi over 2. No, like none of those things were a distance. The arc length. It's getting worse, Mr. Balogh. The arc length, whoops. The arc length, we'll use symbol S, okay? The distance it traveled, say from where it started, where it ended, is equal to what? Does anybody remember? 2 pi r would be the circumference. It's the radius times the angle that you went through. That's the arc length. And a lot of you are sitting there going, I'm dead. No, you're not dead. It's okay. It's going to be all right. Just hang on for the ride. Okay? So there's the arc length. Okay? With the caveat that the angle must be in what units? What's a radian? Not a degree. I like that. It's good. What's a radian? Mathematicians never breach these sensitive subjects. What are the units? So S equals R theta. What are the units of arc length? Meters. Okay? Some length thing, right? We'll just say meters. What are the units of a radius? No. Meters. Right? A radius is a distance, right? It's from the center to wherever the outside edge of the circle is, right? So that's a meter. What are the units of theta? No. Nothing. Right? What do I multiply times a meter to get a meter? Nothing. In other words, radians are nothing. There you go. Did you get that? What's a radian? It's a unitless label. It's not a unit. It's not a unit the same way degrees are not a unit. What's a degree? Somebody decided a long time ago that there were 360 of them in a circle. Right? Does anybody know who to blame? Babylonians. You thought I was going to say Republicans. It's not that this time. Okay? It's the Babylonians. Okay? For them, they did base 60 mathematics. You thought base 10 was hard. Right? But 60 was a very meaningful number in their society and mythology. And so they decided to divide everything up into 60s. And for some reason, we never changed it. But, you know, probably had something to do with them conquering everybody. But anyway, so a radian is the unitless thing. But it feels wrong to just say the angle is 6. Doesn't it? 6 what? Degrees? Radians? Elephants? What's the unit? So we stick it on there, but it has no unit value. And what's the ratio? If you take the circumference of a circle and you divide by its diameter, what do you get? Pi, right? You get pi, which approximates 3.14159, blah, 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 blah. What? What are the units of pi? Radians. But radians are nothing, because what are the units of the circumference? Distance around a circle. Meters. And what's the radius? What are the units of the diameter? It's a distance. Meter, radians. I didn't make up math. If I had made up math, it would have been wrong. All right, so when are we going to have to use radians? Like the mode in our calculator? Yes. Yes. And okay, so I will not be held responsible for you going into your math class and doing a math test with your calculator in radians mode, right? When everything is being given to you in degrees. Sometimes I get the question, Mr. Balogh, how do I know which mode my calculator is supposed to be in? If your angle is in degrees, what mode does your calculator need to be in? If your angle's in radians, what mode does your calculator need to be in? Okay, are we good? Now, it's up to you to figure out how to check that the mode is correct whenever you start something. Okay? I now check every time I pick up a calculator, what mode is it in? Radians or degrees before I start going, right? It got so bad in college for me that I actually bought 2 calculators that were different colors. Right? One was in radians, one was in degrees. They're like, why do you have 2 calculators? Because I'm a nerd. And I can't remember to check. But it was physical. I was able to physically grab one or the other, right? Radians or degrees. The green one was in radians. The blue one was in degrees. All right, so that was sort of a tangent, but not really. It was important, okay? Now, because degrees exist, we do need to know how to get between radians and degrees. These unitless units that we have invented for ourselves. So how do we get from radians to degrees? Is there a conversion factor that maybe we could possibly know? Pi radians is equal to 180 degrees. There's your conversion factor, right? Okay, so just do chapter 1 conversions, right? And away you go. Okay, so we have established so far that we could, on a circle, measure the distance that something goes with an arc length, right? And it would be the radius times whatever the angle is in radians. Okay, but again, like, X and Y are not a good way to talk about where this piece of tape is as it goes around this circle. Okay? We want to talk in a language that is more suited for the angular nature of what's going on here. So we are going to track position with angle theta. The radius is just there. It's along for the ride, isn't it? I mean, it's not like the radius of this thing is changing as it goes around, right? That wouldn't be a circle. That's a different thing, which we aren't going to do in here. Okay? So I can tell you like where my blue piece of tape is. If it starts here and it goes over here, where is it? It's at pi, or 180 degrees, right? Now where is it? 270. Now where is it? 90. Now where is it? I have no idea. Right? So we can tell, we can track. So like, back in chapter 2, we'll call it the old way. And now we got the new way, okay? The old way, we had X or Y to kind of tell us where this thing was, right? Well, for rotation, we're going to use theta instead. And then we went and we changed where we were in time. Either with little d's or big deltas, it doesn't matter. What do we call this idea? This is velocity, right? Direction associated with it, of course, right? But a change in position with respect to time is the velocity. So if we change our angle with respect to time, if I tell you that this thing goes through, I don't know, pi radians per second, or 180 degrees per second, what have I just told you? The angular velocity, right? Okay? A change in position, theta, with time will be an angular, All right, we need to talk. We need symbols. We can't use V. It's taken. We can't use A. We can't use M or T. I, J, and K. Like the whole alphabet's pretty much used up at this point, isn't it? Has anybody noticed that we've been speaking a foreign language so far? What's the foreign language we've been? Not math. What's the other foreign language? Greek. So is there a Greek V? Yes. Okay. Let me tell you what that is not. That is not W. If I hear W in here, I'm going to get mad. Because that is not W. What does a W look like? It's pointy. This is omega. The Greek lowercase, Greek letter, capital omega, right? But the lowercase version looks like that pointy thing that I'm not going to say anymore, right? But this is omega. I want to hear you calling it W. That's an omega. Okay, and that's the symbol we use for angular speed, angular velocity. We'll get directions a little bit later. Okay, what happens if we change our velocity? Yeah, we get this acceleration, okay? So what are we going to change over here? D. There's only two of you that are brave. Omega dt. Back in the days before there were laws, I used to throw pieces of chalk at students that said W instead of omega. You know those little tiny pieces of chalk that would be left over on the board that nobody could ever possibly write with? Okay? They were perfect little ballistic things, right? Somebody would say W and I would be like, boom! Right? It was meant to be funny, right? It stopped being funny when all we had was whiteboards. No, I never threw a pen. Never threw a pen at a student. What are we going to use? Oh, if only there were a Greek letter that was like an A. Ooh, alpha. Looks like a fish. Okay? So those are the symbols that we're going to use, right? When we're talking about angular velocity, angular acceleration. Notice I keep putting the words angular on the front of things, right? So we're talking about circles. What are the units of theta? Like the standard unit of theta? It's a radian. Any degree you get gets converted into radians. What are the units, therefore, of the angular velocity? A radian per second. And what are the units of angular acceleration? A radian per second squared, right? So symbolically, I usually don't put anything down for radians for angles. Sometimes I just write out the word radian. Here I'll do radian per second, and here I'll do a radian per second squared, right? Those aren't rods. Those are supposed to be rads, but I have bad handwriting. All right, so we're going Greek. We're going Greek. There's a couple more things that we need to talk about. I never know where to start. Okay. What is the angular speed of the wheel? 0. How do you know? It's not moving. Good. Right? Okay. Is the angular speed 0 now? No. Is it positive or negative? Oh, okay, well, you just decided that that way was positive, and so therefore, if it's going this way, okay. There's a problem. I'm going to show you the problem. I'm not going to solve it yet, okay? What direction is this going? Clockwise or counterclockwise? First question, what's a clock? Yeah, nobody knows anymore, right? No, okay, right? So if it goes around in the way that a clock would go, this wouldn't be clockwise. What would it be? Counterclockwise, right? Because this is the clockwise direction, the way that hour and minute hands would move on a clock, right? Okay. So you're saying that this is counterclockwise? No, it's not. Do you see the problem? So clockwise and counterclockwise depend on a point of view. Okay? That doesn't mean we're not going to use them. We will use clockwise and counterclockwise like in our drawings, right? Because a drawing tends to lock us to a point of view. But I'll show you later, there's a way to solve this problem so that no matter which side of the wheel you're looking from, everybody will always agree on what direction the angular speed is, or angular velocity is pointed. Okay, so this wheel has angular speed, velocity. What does it have now? More or less? More. How do you know? Go faster, right? What am I doing now? What's that called? Angular acceleration, right? That would be alpha. What's alpha? It's the change, right? So in order for alpha to be happening, what needs to be happening? Needs to be speeding up or slowing down, right? Okay? I can introduce friction. Okay? Or I can apply a, right? We got lots of places to go here. But we'll get there, we'll get there, we'll get there. Okay, the other thing, and I've done enough derivation today, so I'm not going to derive it, even though this one's a pretty quick derivation. There is a Google Translate algorithm that can get you back and forth between linear ideas and angular ideas. Here it is. The velocity is equal to the radius times omega. This would be a tangential velocity. I'll explain in a second. The tangential acceleration is r times alpha. Again, this is how you get back and forth between, say, v and omega, or alpha and acceleration tangential. The centripetal acceleration, you remember centripetal acceleration from way back in the days? Chapter 4, v squared over r, can also be written as r omega squared. Okay, I've introduced a couple of things here. Let's talk about tangential. So if we've got the wheel going around in a circle like this, okay, and it's going counterclockwise for you, right? If I sort of freeze frame the wheel and I just look at this mass right here, okay, at this instant, which way is this wheel, this part of the wheel going? It's going straight up, right? And as it rotates around and gets here and I do a freeze frame, which way is it going? To the left, right? If it goes over here, down, right? If I sort of isolate a point, I think like I'm an ant riding on this bicycle wheel or something, right? At an instant, the ant will always have a tangential velocity, meters per second, right? It has angular speed, right? But the tangential speed it has depends on what? Where it's at. Be careful. Is the tangential speed on this side different than this side? The velocity is different because the direction is different. I'm asking about speed. It's the same, isn't it? But what happens to the tangential speed if the ant is riding down here on the hub? It gets lower. Why? Because the radius is smaller. Do you see it? Omega at the center versus the outside is the same. We're going through the same angle at the same time. So omega is independent of how far away you are from the axis of rotation. But the tangential speed gets bigger the further out you go. On the merry-go-round, why do all of the kids want to be on the outside horses? Because it's faster, right? Okay? It's because the tangential speed out there is bigger. Angular speed's the same for all the horses. How do you know that? Because the merry-go-round's not flying apart, right? Okay, but the tangential speed will be different. Okay, tangential acceleration. When we did circular motion before, things going around in circles, what direction was the acceleration pointed? Towards the center, right? In order for something to move in a circle, the acceleration has to be pointed towards the center, because there's a force that pulls it in towards the center. Well, now, not only do we have a centripetal acceleration, we're going to have a tangential acceleration. Centripetal acceleration keeps the object moving around in a circle. The weights on this tire are being pulled towards the center, right? Constantly. Otherwise, what do those weights want to do if they were left alone? Just move in a straight line, right? Okay? So, to get them to go in a circle, a force is applied directly towards the center, centripetal acceleration. But if I slow the wheel down, that was not a centripetal acceleration. That was a tangential acceleration. Speeding up or slowing down the wheel, alphas, okay, are related to tangential accelerations directly. We do have a Google Translate to get between centripetal and omega, but notice the only way to get from alpha to A is to be talking about the tangential acceleration. So if this wheel is going around like this and I slow it down, at this point, what direction was the acceleration pointed? It was down. If this point is moving up and I apply an acceleration down at this point, what will happen to the wheel? It'll come to a stop, right? So tangential things are related to the circular motion. Centripetal is still there. It has to be there, okay, in order for things to go around in circles. But remember that there's now two. Okay. Let's talk about that whole direction thing. The way that you overcome this whole, well, this looks like counterclockwise, or it looks like clockwise, depending on what your point of view is by using something called a right-hand rule. This is simply a standard, think of it like setting a coordinate system almost for rotation, okay? Everybody across the world, like you go to anywhere, any other country, you might not be able to speak the language. If you do a right-hand rule and they're an engineer, they're going to be totally understanding what's going on, okay? So what you do, okay, if I take this wheel and I spin it, right, what you are going to do is you're going to take your right hand. Everybody raise your right hand. Repeat after. No, we're not going to. Okay. I'm just making sure everybody knows which one is their right hand. Put them down now. One of the preeminent philosophers of our age, incredible thinker, very deep, whose name is Winnie the Pooh, said, see if I can get the quote right, I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference. That's deep. That's deep. All right. So you take your right hand. What you're going to do is you're going to do a hitchhiker movement, right? Where you don't ever hitchhike. Take an Uber instead. How's that? Anyway, we now pay for strangers to come and pick us up. So wrap fingers around in the direction the wheel is rotating, and your thumb ends up giving the direction for the rotation, right? So it doesn't matter if I'm looking from my side. If I wrap it around, my thumb ends up pointing in the same direction that you guys are doing it. Let's do it the other way. How would you do a right-hand rule here? Wrap around, thumb points that way, right? Okay? This gets even better. Which way is the angular velocity pointing? Up. Right? Which way is it pointing now? That way. Which way is it pointing now? That way, right? We can always specify a unique direction for the angular velocity of this wheel, no matter where it is in three-dimensional space. So, the magnitude is omega, the direction, right, would be set by the right-hand rule. So that gives us a three-dimensional vector in space. We're not going to do three-dimensional vectors. We're just going to keep everything two-dimensional. So typically what we do is we draw a circle, and then we draw a direction to indicate positive, and that direction can be either clockwise or counterclockwise, as we see it on the page. But we can also do in or out of the page and all that kind of stuff. So that's your first encounter with the right-hand rule, and we'll leave it at that, okay? There will be a quiz at the start of next class, a real one. So be prepared for that. I will see you on Friday, maybe in Grasp. But if not, I'll see you next Tuesday. Have a great weekend.